Welcome back. Glad to see you all here today. I hope and I trust that you've gained something so far from the two sessions we had, and that this one will further it. And once again, I have another prayer that I'd like to say that I hope will be very relevant to what we're going to be seeing today. In the name of the Father, and the Son, and the Holy Spirit. Amen. Heavenly Father, we come before you in heartfelt wonder, probing the magnificence of your majestic creation. We stand in awe. It humbles us to ponder our smallness in comparison with the grandeur of your handiwork. And we tremble knowing that you have given us minds that can comprehend your magnificent universe. We pray for a heart that seeks the inspiration your creation offers. Open our hearts and minds to your will in the beauty of the natural world you have given us and in the exercise of the dominion you've graciously granted us within it. Bring us together in reverence for your creation. May the awe of your magnificent handiwork unite us, transcending our differences. May we be inspired to manifest our love with those with whom we share your creation and so truly reflect your glory. In Jesus' name, amen. In the name of the Father, and the Son, and the Holy Spirit. I was requested to put out some notes summarizing the other sessions, and those were put on the table. I also summarized this session. I'll just ask you a question. For those of you that haven't, would you like me to read the summary of last week or just go? Just go. Okay, good. You can read them on the notes, and that'll be it. Okay. Last week, we concluded with a reference to the fact that there is emerging a new renaissance in science, and that renaissance is catalyzed primarily from the things that came from the discovery that the universe had a beginning, the Big Bang. That it was a universe that had an intense history and one in which was clearly going from simplicity to complexity. And we looked at the life of the stars and saw the special role that the stars have in their living and in their dying. They are creating all that's necessary for us to have a place to live and to be in the universe. And today we're going to continue to explore this rapidly expanding evidence supporting this wonderful metaphysics of creation. And here I go again. You're going to hear philosophy a lot again, okay? Because it is the essence of what's going on. So I'll do that again. So we're back. This is I had the same title last week, The Renaissance of the Teleological Universe. Again, just to define the terms, teleology is all about purpose. And the physics, the metaphysics, that is the reality that we understand creation, is that it's a creation that has a purpose. And that's fundamentally important. That's contrary to postmodernism, which says it has no purpose. It's meaningless. So today, what we're going to do is explore one of the elements of the universe, which is its incredible precision and the fact that it's so comprehensible by us. But before I do that, or in order to do that, I'm going to set the stage. And I'm going to set the stage with a story, because this story will teach us how we can understand this. It'll serve as a basis for interpreting and understanding a lot of what I'm going to be presenting. And it's the story of James Maxwell, James Clerk Maxwell. Anybody ever hear of him? Just very few people, huh? He's not a name that pops up, but he's one of the greatest scientists who ever lived. And I mean in a handful, that small. James Clerk Maxwell. I told you last week a little bit about the great generation of scientists in the first quarter of the 20th century. And I mentioned Max Planck, Albert Einstein, as being great figures. What I'm doing now is going back a little before to the man who inspired them and telling you the story of Maxwell and how he relates to those greats who later followed him. Maxwell was working at the time of the American Civil War in Scotland and then later on in England in small colleges. And what he did was absolutely revolutionize our understanding of a broad range of the forms of energy that exist, that we perceive. He advanced the work greatly of what Michael Faraday a few decades later had done when Faraday found that magnetism and electricity were related, and he developed very crude little experiments to show that you could create motion from magnetism and electricity. In other words, a really, really, really simple little tiny electric motor that he was able to generate, just a spinning little wand in a pool of mercury. But he proved something. And he had no theoretical basis for it. What Maxwell did was determine that theoretical basis. He saw it. And he discovered the relationship, and it became the great theory of electromagnetism, something that is the fundamental basis of modern life. That's one of the things he discovered. And that would be great enough, but he discovered two more. The second was he discovered the nature of light. And he found that light was electromagnetic radiation also. That was the second thing. And the third thing he did was discover the relationship between all these forms of energies and came up with the electromagnetic spectrum. Ever seen this? For those of you who aren't too familiar with it, it's really, really important. I'll go over here to this. I'll go over here to this one and point it out. What it does is put all the things that you and I know exist in the world because we use them and puts them all in the same scale and says they're all basically the same thing. Qualitatively, there's no difference. The only difference is quantitative, and that is just what the frequency or the wavelength, depending on how you want to look at it, of the waves are. But it covers everything on the spectrum, from the highest powered forms of radiation, the gamma rays, down to the weakest, down beyond the AM radio scale. Up here in the gamma rays, that's the stuff that goes on in stars and in a thermonuclear bomb. That's what goes on. Everybody knows what an X-ray is, and you all know that you can't get more than a fraction of a second exposure to it, right? Because of its power. Ultraviolet, a little bit dangerous, but nothing that'll kill you unless you get quite a bit of exposure. Then the visible, the infrared, you all know microwaves, and my goodness, radio waves. Microwaves are what our cell phones work on, so my goodness. And then radio waves, everything else. So all this comes from Maxwell. He's the one who discovered this. The electromagnetic spectrum literally changed the world. It integrated all these various ideas and made them accessible. And Maxwell's work was completed in the early 1870s. He died a young man at age 48. But immediately after his discoveries, everything took off. That's when the age of the things you do know, because the entrepreneurs and the inventors came along. Thomas Edison, the light bulb. George Westinghouse, who came up with alternating current, which was a safe way of distributing electrical power over a large distance, which is essential for modern life. William Shockley, the inventor of the transistor. He's holding a little one in his hand. If you remember the old transistor radios, okay, how crude they were? Now we have billions and billions of them on a chip that small, right, running our life. Tim Berners-Lee, what did he do? The internet, the World Wide Web, actually. The internet came from the government. It was the ARPANET, but is what gave us the internet, us common people. And they all did this. Einstein made the comment when he was asked one time about the greatness of his work, and the question was, are you standing on the shoulders of Newton, the great founder of classical physics, of motion and gravitation? And Einstein said, no, I'm standing on the shoulders of Maxwell because of everything he did. It turns out Maxwell's equations did not work in one circumstance. And it became an incentive for another great discovery. And this is where Max Planck comes in, the fellow I told you about. The situation that didn't work was something called blackbody radiation. It's just, blackbody radiation is what heated bodies, the energy that heated bodies give off. Think of a blacksmith sticking a rod of iron into a fire, and it glows, right? Blackbody radiation is the science of studying the energy that's given off because it's heated. And it studies the spectrum of the energy. Where in the spectrum does that energy come if you heat an object on that scale, spectrum? Turns out that Maxwell's equations failed predicting blackbody radiation. Worked everywhere else. But there was something basic that was missing because it should work. And Planck said, why doesn't it work? And that's what set him thinking, and he came up with some inspiration. And Planck reasoned that matter, this is 1900 now, when Planck comes up with his work, he reasoned that matter, which even though they didn't know much about atoms, they still knew there were atoms. They didn't know about a nucleus at that point at all. Okay, they just knew that there were atoms. But he reasoned that atoms were very tiny, discrete bits, right? They weren't continuous. There was a level at which you could find discreteness in matter, and it was atoms. And he reasoned that energy could be the same. It looks continuous, but if we got small enough, it could be discrete. And he reasoned that if that was the case, then the reason this black body didn't work is because it could give off different little packets of energy at different rates. It wouldn't have to do it continuously. Anyhow, this theory became tested, and it worked. And this theory of Planck, of these bits of energy, was called quanta. And quantum theory, that energy is at a small level, particles, became the basis of physics in the 20th century. You've probably all heard the term photon, right? A photon is just a small quantity of energy. We usually think of it as light energy, but that's what it is. And of course, then Einstein would go on the next step, and he would do his work. The beauty of the work that Planck did is that the result of his work is that if energy was this little particles, then because of the electromagnetic spectrum, it was clearly easy that the energy of every little particle was simply proportional to its frequency, because that's where the energy is. The higher frequency is higher energy. And all you had to do was figure out some constant, which became known as Planck's constant, h, in that formula, E equals h nu, and you had the energy of radiation at any scale on the electromagnetic spectrum. And this, like E equals mc squared, became one of the great equations, the beautiful, simple, great equations of infinite utility in modern science. And what I'm telling you in this story is the arc of a bit of history of three great scientists who had a lot in common. They were men of the classical mold. They were men who were highly philosophical in their approach to science and who did this work. And the results that they produced were of amazing utility. In all of this work, in that short span of time, the understanding of our universe proceeded to an integrated, holistic view of magnetism, electricity, matter, and energy, all unified in a conceptual view that led to so much great progress from having that understanding. It was philosophically sound, and its mathematical expressions were clear, concise, and eminently useful. And the other part of the philosophical aspect of this is that it underscores something about human beings, human nature, the universe, and knowing nature. It underscores that we're meant to and we can discern what Galileo called the book of nature. It is intended for us to do that. The tools are there. So there's two profound realities that come out of the work of Maxwell, Planck, and Einstein with regard to that book of nature. One of them is mathematics itself. The fact that mathematics functions so well in interpreting nature. The second one is the fact that in these equations that come out of this work, there's always some numerical constant that's in the equation. You saw in the Planck relation, h was that factor. You know, in Einstein's equation, it's c squared. That's the constant that's in the equation. And it turns out that we're going to go through this in more detail later on, that those constants are incredibly interesting and reveal so much about the precision in the design of the universe. But first, I want to go and take a look at mathematics and take a closer look at its importance. And then we're going to look at the fact that we can comprehend. Those two things, mathematics and comprehension. I've got a little construct here that I put together about mathematics. Oops. Did I go backwards? Yep. Okay. This is my own idea. So if it's wrong, I don't want to blame anybody else. But I think there's a telos to mathematics. Telos, again, being purpose. The purpose of mathematics in this. And the first is that the laws of nature and mathematics are both non-material entities, and both are unique and accessible to man. Right? With me so far? Third, that mathematics do effectively describe the laws of nature. And fourth, that because of all this, man is capable of comprehending both nature's design and nature's laws. Both. And that is the great innate designed purpose that I think we can say is in the universe. Now, the effectiveness of mathematics is clearly an issue that separates the classical scientists like Maxwell, Planck, and Einstein from what I previously described as the scientism that we have today. And and it separates them whether or not they're theists, by the way, because that's really not a factor here. Oh, I'm sorry, my clicker was back one, sorry. In 1960, a man by the name of Eugene Wigner wrote a paper that became a stake in the ground, which has since then been a point of distinction between the two camps. Wigner's comment was that mathematics is a miracle which we don't, we neither understand nor deserve. What I'm going to do is play a couple of videos for you to explore that. The first video is a video from the viewpoint of of a classical scientist, or no, from the viewpoint of a theist. This is from William Lane Craig, and some of you certainly know him in his point of view. And it will point out the distinction in how the two sides of science view mathematics. And I do want to say that the bigger side is the one that disagrees with this video. Okay, that's the bigger one.
Why does mathematics work? Think about it. Mathematical entities like numbers, sets, and equations are non-physical and abstract. They can't cause anything. Yet, for some reason, the physical universe operates mathematically. As Galileo put it, the book of nature is written in the language of mathematics. Scientists do not use mathematics merely as a convenient way of organizing the data. They believe that mathematical relationships reflect real aspects of the physical world. Science relies on the assumption that we live in an ordered universe that is subject to precise mathematical laws. Thus, the laws of physics are all expressed as mathematical equations. For example, Pythagoras discovered that when a vibrating string is shortened by half, it plays the same note one octave higher. Isaac Newton's observations led to his discovery of the law of gravity, a mathematical relationship expressed as a simple equation that enabled us to enter the space age. Mathematics enabled astronomers to pinpoint the location of a previously undiscovered planet. And James Clerk Maxwell used mathematics to predict the existence of radio waves. Albert Einstein, working with theoretical mathematics developed 50 years earlier, formulated his general theory of relativity, a pillar of modern physics. His calculations were later confirmed during a solar eclipse, when Arthur Eddington observed light from distant stars bending around the sun. Then, Peter Higgs used mathematical equations to predict the existence of an elementary particle. It took 48 years, billions of dollars, and millions of man-hours for experimental scientists to finally detect the Higgs boson. How do we explain the astonishing applicability of math to the physical world? In 1960, the Nobel Prize-winning physicist and mathematician Eugene Wigner published an article that stunned the scientific community entitled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." Wigner concluded that the effectiveness of mathematics is a miracle, which we neither understand nor deserve. Why is mathematics so effective? Philosophers who address this question fall into two camps. Naturalists, who believe that all that exists concretely is space-time and its physical contents. They exclude supernatural causes. And theists, who believe in a God who created the universe. Naturalists cannot provide a reasonable explanation for why mathematics applies to the physical world. It's just a happy coincidence. But this is no explanation at all. At most, naturalists can say that it's not surprising that math applies to the world because the world itself just happens to have a mathematical structure. So, of course, mathematics applies to it. But this explanation is unsatisfactory for two reasons. First, a great deal of mathematics in science cannot be physically realized. For example, imaginary numbers and infinite dimensional spaces. Although these concepts are useful, physical reality cannot possibly have the structure they describe. And second, this answer still doesn't explain why the physical universe has such a stunningly elegant mathematical structure. By contrast, for theists, mathematics works so well in the physical world because God has chosen to create the world according to the plan he had in mind. The first-century Jewish philosopher Philo of Alexandria offered this analogy. When a king wants to build a city, a trained architect first designs in his mind a plan of all the parts of the city that are to be completed. Then he begins to construct the city out of stones and timber, looking at the model and ensuring that the material objects are built according to the plan. Mathematics and physics work so well together because the same mind that designed the universe on a mathematical model also built the universe on the same mathematical model.
So that's the point of view from the standpoint of a theist. I'm going to play another video for you here, showing someone from the more common perspective of what's out there in the world today. And this is from a series by Robert Lawrence Kuhn called Closer to Truth. Some of you may have watched this fellow. He's been doing it for about 15 years, and he's put out hundreds and hundreds of interviews, maybe thousands almost, with scientists up and down the line. I've watched several hundred of his videos over the years. This particular interview is with a guy by the name of Jim Holt, who is a philosopher of science, but is in the scientism school. And this is kind of typical. And I just want you to see, after you've seen this and you've seen the reasoning, here's the other perspective.
I mean, there are those who believe, like Sir Roger Penrose, believes that the world is, in a sense, really made out of mathematics. Hartree Field argued that you can do all of science without positing any mathematical entities, that it's very convenient to use mathematics to do science. So these are the two extreme positions. And in that the continuum of positions in between, I would feel more comfortable being away from Sir Roger Penrose, because his belief that the world is made out of mathematics is a kind of reflection of Plato's idea of reality. And I think that's a beautiful conception, but I think it's slightly religious, and I prefer to stick with a more hard-headed empiricist.
So you see where the dividing line, huh? The metaphysics of the divine is where the line gets drawn. They just can't take it. It's just ontologically unacceptable, which means in their seeing of what is reality, what is being, nope, that doesn't exist. So that gets done. And that's the typical response. He's a good philosopher. He's well-read, and he writes very well. And so he's very typical. Okay, that's mathematics and its wonderful relations. Now, let's switch gears to the comprehensibility of the universe, which is the other amazing thing. You probably remember saying this, I referred to it, and it's one of the most famous sayings of Einstein, that the most incomprehensible thing about the universe is that it is comprehensible. I always thought that was a wonderful point of view, and the more I read it, the more I appreciated it. But it really asks the question, doesn't it? Why? Why the comprehensibility? Einstein doesn't address that. He just marvels at it. Well, what I'm going to do is go back actually to that same episode of Robert Lawrence Kuhn's interviewing people, scientists, on the same question. And I'm going to show you another interview with a physicist whom I greatly admire. His name is Paul Davies. The thing I admire about Paul Davies is his courage to resist the monolithic culture that he's in. Davies is not a religious person. He's just a person who looks at what he sees, evaluates it, and says, I don't see the evidence. And everybody disagrees with him, and he stands up. So this is an interview where Davies is being interviewed by Kuhn and asked the same question about mathematics.
I ask a visionary scientist unwilling to reject the role of the human mind in the nature of reality, unafraid of the deep waters of teleology, mind, and meaning, physicist Paul Davies.
The mystery for me is not why does mathematics work in the world, but why does mathematics that human beings have the ability to understand and manipulate work so well in the real world? Why is it that this species, Homo sapiens, has evolved the capability of doing this type of abstract reasoning and doing these mathematical procedures, some of which are quite hard, in a way that is so extraordinarily effective in grasping the nature of so many physical phenomena? Now, a lot of people just shrug this aside. But I don't think there's anything in our evolutionary history that compels human beings to develop the cognitive architecture necessary to do this. Our brains, our minds have evolved, like our bodies, to survive in the proverbial jungle. And so, of course, it will be useful to be able to count and work out angles and so on. But there's absolutely no reason why we should have the level of mathematics necessary to explain, for example, the nature of black holes or the structure of the hydrogen atom or anything like that. These are things beyond any sort of reasonable survival value. So is it just a coincidence that the mathematics that we evolved to cope with just for basic survival also just happens to work so well in so many areas of reality? I don't believe in coincidences like that. I think it means that the human mind has evolved, and the mind, not the brain, I'm talking about the human mind has evolved to somehow mirror the nature of reality in a very deep way. I think it's a non-trivial fact. It sounds a little bit mystical. It sounds like somehow we are meant to be here, or that we are players in the great cosmic drama in this very fundamental way. Yes, I think we are, and it's one of these facts that I regard as giving huge significance to human life.
You notice at the very beginning of this video, the thing he did was ask the big questions, which is something you'd never see from the other side. Why? Why? That's the pursuit. That's the metaphysical interest that has dwindled and died. I'm going to go on with two more videos with Davies here. Robert Owens-Kuhn is going to point out that he is very much unlike his peers in the next one, and you can hear his response. He acknowledges, I am in the minority, but I see implications.
You are distinctly in the minority among at least the physicists and mathematicians and scientists, a place that you apparently like to inhabit.
Yes, I freely admit that most of my colleagues would not agree with me. On the other hand, they don't give very coherent accounts of why mathematics is so useful in physics either. And so I often will provoke them by saying things like, well, where did the laws of physics come from, and why do they have this elegant mathematical form that they do? And they really don't have an answer to that, because I think there is something about the emergence of life and intelligence that plugs into this deep nature of reality. So you're seeing this as a sort of quasi-religious view. It's very far from traditional religion, but it is a belief that in this great scheme of things, human beings are one representative of this deep place that life and mind has in the unfolding scheme of the universe.
And one more video in which he draws conclusions about this effectiveness of mathematics. And here is where he gets where I like to be, teleological.
So you have taken the unreasonable effectiveness of mathematics as a deep probe of what reality is and sees more meaning and purpose in the totality of realities.
I don't like brute facts. So people can say, well, that's just the way the world is. But I want to know, well, why is it that way? And I just think this connection between our ability to describe the world through human mathematics must say something very profound about the nature of the human mind. And so this is built very deeply into the structure of the universe, I claim.
You see, what he has done, he's made the same connection. The universe and the human mind have something. There's something deep in the universe. There's a deep place for the human mind. How else can we explain this? He's not coming at that from a religious point of view. He's just coming at it from looking at evidence and just asking the big questions and doing it. That's hard to do. And I admire him for doing what he does. Okay, that's the little look at mathematics and look at this comprehensibility that we have. And they're both wonders. The wonder that mathematics works so well as the language of science, and the fact that we can comprehend the universe, its laws and its design, and use mathematics to see what's in the book and read the book of nature. Those are really wonders. I'm going to shift gears now, and I'm going to shift to what I said earlier about those scientific equations and the fact that there was a constant in them, and that those constants were themselves something of great interest. I'm going to spend some time exploring that. This is more than just getting the numbers right, getting the equation to balance and just finding some exact value. It turns out that more and more accurately determining what those constants of nature has a huge amount to tell us about the fabric of nature, about its precision in its design. And again, for here, I'm going to play another video to show that if these constants weren't precisely what they are, we wouldn't be here asking the questions about the constants.
The existence of our entire universe and everything in it comes down to about 30 numbers. Physicists call these the physical constants. Now, these numbers, as I understand them, are fixed values of a fundamental physical condition we find in our universe. For example, the force of gravity or the expansion rate of the universe, right down to the subatomic, such as the mass of a proton or electromagnetic force. Now here's the amazing part. Each one of these numbers are so perfectly precise and so balanced with one another that if any one of them were off, plus or minus the slimmest fraction, in some cases literally this much, there would be no life and no universe as we know it. For example, if the gravitational constant were just a hair bigger or smaller, the stars of the early universe would be too hot or too cool to produce any life-essential elements. If the electromagnetic force were just a hair stronger or weaker, atoms can form into molecules, and the entire universe would be a giant cloud of subatomic particles. If the mass of a tiny little proton was just a tiny bit bigger, there'd be no hydrogen, which means no hydrogen stars, which means no carbon and oxygen made in those stars, which basically means no water and no biology.
It's pretty amazing, isn't it? And not only that, the ability to look into the sky and see further and further back in time, which is a capability we have, has enabled us to see more and more accurately what the universe was like literally seconds after the Big Bang. The cosmic microwave background is one of the things which has helped so much, even though that's more than just a few seconds after the Big Bang. And what's been learned about that is something that's in addition to the constants of the universe as they are now. What was learned by those studies is what the initial conditions of the universe were in that very, very formative stage right after the Big Bang. In other words, what were the conditions that existed then that led through the laws of the universe to where we are now? Because if the initial conditions weren't what they were, then with the laws operating, something different would have come out, right? So how precise was it necessary to have certain conditions right at the moment of creation, essentially, okay? And for that, I got a couple more real short videos about two of these initial conditions.
Omega is the density parameter in the universe at the time of the Big Bang. Now, this gets a little complicated. Basically, it means the ratio of the mean density of the universe to the density just needed to overcome cosmic expansion. I know that sounds like gobbledygook, but stick with me. Think of standing at the bottom of a well and throwing a rock up from the bottom so that it stops at exactly the top of the well. If you don't throw it hard enough, it doesn't make it to the top. If you throw it too hard, it leaves the well. You have to throw it just right. Omega is about how the universe expanded at the time of the Big Bang. Not enough force and the universe would have collapsed back on itself in a big crunch. Too much and the universe would have blown itself out too fast and nothing would have formed. It had to be just right. That's omega. Today, that ratio, omega, is 0.3. But the real important thing here is that at 1 second after the Big Bang, it could only have been one, or what scientists call unity. If it were off of unity by 1 part in a quadrillion or 1 part in a million billion, the universe would have either flung itself out too far, too cold, and too fast, and nothing would have formed, or it would have collapsed upon itself.
Another one of those amazing things, huh? And then there's one more. That was the density at the point of the Big Bang, okay, how compact it was. Then there's one other factor, and that's the degree of non-uniformity. Just however non-uniform it was, turns out to be very, very important.
Q is all about texture. And at the very moment of the Big Bang, the universe, still microscopic in size, wasn't completely smooth. It had a texture to it. The amplitude of the texture was 1 in 100,000. If this ratio was smaller, the universe would not have had the texture to allow clumps of gas to turn into stars and planets, attracted by each other's gravity. If Q were any larger, there would be huge pockets of mass with massive gravity fields with no chance for life. You can still see this texture in the pictures of the cosmic background radiation in the universe. The shifts in color show the shifts in texture. And by texture in the universe, we mean galaxies and quasars and black holes and little planets with oceans and Episcopal churches.
This is an Episcopal priest recording something. Everybody that's on this team is okay with me. I told you, I like them all. Now you might say, how do you say no to that kind of evidence, right? It seems pretty darn strong, huh? And yet there is. There's vociferous reaction that says no, 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 from most of the people involved in academic science today. That's the reality. I'm not going to get you into all the responses. I don't want to take the time to do that. It's not the purpose of why we're here. But I do want to let you know where the thinking is primarily going. The number one idea that is out there to explain what can be the case if none of this is really the case in their eyes. And that's something called the multiverse. You've probably heard that, huh? Okay, you'll see that introduced in this video.
What is the best explanation for this astounding phenomenon? There are 3 live options. The fine-tuning of the universe is due to either physical necessity, chance, or design. Which of these options is the most plausible? According to this alternative, the universe must be life-permitting. The precise values of these constants and quantities could not be otherwise. But is this plausible? Is a life-prohibiting universe impossible? Far from it. It's not only possible, it's far more likely than a life-permitting universe. The constants and quantities are not determined by the laws of nature. There's no reason or evidence to suggest that fine-tuning is necessary. How about chance? Did we just get really, 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 really lucky? No. The probabilities involved are so ridiculously remote as to put the fine-tuning well beyond the reach of chance. So, in an effort to keep this option alive, some have gone beyond empirical science and opted for a more speculative approach, known as the multiverse. They imagine a universe generator that cranks out such a vast number of universes that, odds are, life-permitting universes will eventually pop out. However, there's no scientific evidence for the existence of this multiverse. It cannot be detected, observed, measured, or proved. And the universe generator itself would require an enormous amount of fine-tuning. Furthermore, small patches of order are far more probable than big ones. So the most probable observable universe would be a small one, inhabited by a single, simple observer. But what we actually observe is the very thing that we should least expect: a vast, spectacularly complex, highly ordered universe, inhabited by billions of other observers. So even if the multiverse existed, which is a moot point, it wouldn't do anything to explain the fine-tuning. Given the implausibility of physical necessity or chance, the best explanation for why the universe is fine-tuned for life may very well be it was designed that way.
Okay, and at the same place. I told you there are other speculative ideas that I don't want to get into, but they all share something in common with the multiverse. And here's what they are. None of the ideas can even in principle be tested. So they cannot be falsified. So what's now mainstream cosmology is largely what everyone would have said is not science. It's either philosophical reasoning or just speculation. But that's where science is. And as you might even imagine, just from that, within the scientific community, one of the most recent things that's happening within the last decade especially, and in the last few years especially, is that the criticism from within the community to that is beginning to rise. What are we doing is the criticism. Are we doing science anymore? That's happening. So that's where it sits, okay? And with that, I'm going to switch gears, all right? And do something now that's really different and I hope fun. We've been talking about the wonderful teleological aspects of the universe, its incredible precision, everything to build life. Now I want to switch gears and look at how the universe in many of its elements, not all of them, I haven't got time for that, but I'll look at several elements as to how each element now in this universe of design functions to promote life. That each design of each element is so fit for life is the term that one of my heroes, Michael Denton, who is the big investigator in this area, uses. It's the fitness for life of all of the elements of the universe. And I'm going to use simple elements that we're all familiar with, okay? I'll begin by just starting again where science is right now in its perspective, and it's something called the Copernican principle. Everybody knows who Copernicus was, but Copernicus, of course, is known for advancing the idea that it's the sun that's the center of the solar system, not the Earth, and the Earth rotates around the sun and not vice versa. That has been extended in secular science to a principle that says we're not special. And it's been extended so far, it says that there's really nothing exceptional about us at all. We're just mediocre. That's all. And Carl Sagan, I'm backwards slide again. That's the Copernican principle. And then Carl Sagan, in his lyrical way, I suggest, extended it and says, who are we? We just live on an insignificant planet, a humdrum star, in a lost galaxy tucked away in some forgotten corner of the universe. That's who we are. And that's, in a lot of minds, that's the practical application of the Copernican principle. And again, it couldn't be more different from the other perspective. So we're now going to explore the ways that the elements are designed for life and that intentionality. And there's so many things that I could choose to do that as I was sitting back this week thinking, okay, which ones am I going to pick? It was really a problem. Where do I go? I got so many choices and not much time. And so what I did was pick up on a little piece of inspiration that I had, and this clarified my choices. Some of you may remember this picture. A lot of you are old enough. Maybe you remember Christmas 1968. Everybody was watching Apollo 8. go around the moon and sharing with us and talking to us. And it took several days after they came back for this high-resolution picture to get to us. They just had low-res TV that we saw. But we all saw this beautiful picture, and it was awe-inspiring. Poems were written about it. Songs were written about it. It was called Earthrise. It was a perspective of our Earth that we had never had. And it sort of takes your breath away the first time you see it. And I remember that. And so I decided that would be my inspiration and what to talk about. What I'm going to talk about is what's in that picture, the elements that are there. The elements are the two great things you see on the Earth. The things you see are the beautiful blue that colors our planet, the water. And the other you see are the clouds in the sky in our atmosphere. Our water is a unique characteristic of our planet. Our beautiful atmosphere is another unique characteristic of our planet. So I picked those two. And in the foreground is the moon. And even it is a big character, a big player. And finally, there's one more thing in that picture, and that's the light from the sun that's making that picture possible. So I picked those four things. And I want to just talk about how those are all each fit for life. And then next week when we get here, I'll have a few more, okay, and do that for you. So let's talk about light. Well, let's go back to Maxwell's electromagnetic spectrum and talk about the light from the sun. And this, again, is just the same kind of a chart that you saw from Maxwell, where you have different wavelengths on the electromagnetic spectrum. Only it's turned around. Okay, they're swapped left side and right side. And all that's displayed in this chart is the visible light that you and I can see from. And that red line, the sort of parabolic line right here, is the spectral curve of the sun's energy on this curve. So that's what the sun gives to us. And you could see that what we get from the sun, almost half of it is visible light, 44%. About 49% is in the long wavelength, the infrared, and about 7% is in the ultraviolet. And obviously, that's important, because that's how we see. We get the light from the sun to the sea and do that. The other thing that's important from the sunlight, though, is that there is a little bit of infrared in there, and if we didn't have that part of the solar spectrum, the Earth would be too cold for life. The infrared energy is picked up by the sea especially, and warmed and creates the ocean currents that warm the Earth and maintain our environment. So both are important parts of it. Okay, let's go from the sun then to the atmosphere. Before I get to the atmosphere, I got to tell you another story. This one much, much shorter. Remember the story I told about the stars? That they're living, and in their dying, they create the elements that we are composed of. Well, there's more to that story, as far as we're concerned, than just what the stars do, because what had to happen is that some of those stars had to, in this area of the Milky Way galaxy, had to pave the way for us. And our story is that did happen. Multiple stars lived and died and created some sort of a nebula of dust and gas in this part of the Milky Way billions of years ago. And that gravitationally started to form and swirl. And out of this, our solar system came. 4.5 billion years ago, the state of that swirling was that this planet Earth was a hot, rocky mass, a glowing red mass, kind of like that iron that a blacksmith would stick into a fire. That's what it was. About a billion years later, the very first life appeared on this planet. It was called cyanobacteria. Doesn't exist anymore. There was no oxygen at all in our atmosphere. The only thing in our atmosphere is what this hot, igneous planet was throwing up in eruptions and volcanoes, and that a lot of gases were being generated by volcanic activity, and that it was a lot of carbon dioxide, methane, and other things, sulfur dioxide, all kind of noxious things. The cyanobacteria could live on those, however, and the thing about cyanobacteria is its byproduct is oxygen. It eats the other stuff and produces oxygen. And slowly, over 1 billion years, the cyanobacteria produced an oxygen-rich atmosphere. And out of that came the kind of life that we know. That was 2.5 billion years ago when an oxygen-rich atmosphere, a truly remarkable thing, took place on this earth. And it was only 600 million years ago when the first form of life, scientists believe, began here on Earth. So that completes the story here, okay, as far as our atmosphere goes. We go back that far. And also there's some other aspects of this story too. One is that an oxygen-rich atmosphere, astronomers believe and astrophysicists believe, is a very, very rare thing. We've got it because of our amazingly peculiar history. Another thing is that if the Earth weren't almost exactly the size it is right now, if we're a little bigger or a little bit smaller, we wouldn't have that atmosphere. If it were a little smaller, we would have retained way too much of the carbon dioxide from its earlier years. And everybody now, in this time, knows about global warming, right? Okay? We've got like 400 parts per million of carbon dioxide in our atmosphere, okay? It would have been several percent carbon dioxide in our atmosphere, hundreds or even thousands of times the concentration we have now. And what we would have is what Venus has. I don't know if you know this, but Venus is a little smaller than Earth, and Venus has an atmosphere of carbon dioxide, and the surface temperature on Venus is almost 900 degrees Fahrenheit. 900 degrees. Okay? That's what it would be. Too large, if the Earth was larger than it is now, then it would retain the hydrogen and the helium and also methane, which is a lighter gas, and then for a different set of reasons, life would be unable to be had. So the size, it turns out, was very important. Now moving ahead, I want to show you another graphic, and once again, the electromagnetic spectrum, okay? Thing you saw with the same scale displaying it. This is the transmission of light by our atmosphere. I showed you what the sun generates, right? It generates that visible light. To get to us, that visible light has to go through the atmosphere. The atmosphere doesn't let all of it in. What does it do? These bands indicate how much light gets to the Earth. This is radiation getting to the Earth. This is radiation not getting to the Earth, okay? Along this spectrum. Here's the high energy stuff. Here's the low energy stuff. Here's the visible stuff. And what you see is that this atmosphere of about 80% nitrogen and a little over 20% oxygen is such that it absorbs all the high energy stuff that comes from the sun and outer space before it gets to the Earth. It lets the visible light get here, and it lets the radio wave light get here. This is really important. I don't think I have to explain to you why that's important, right? Why the visible light gets here, because we need that. I might even go over here and say it does let a little bit of ultraviolet in, as you can see right here. So that's why you can get a sunburn, okay? But that ultraviolet also functions because it helps create the ozone that combats other more dangerous ultraviolet that would hurt us. So there's a function in that either. But it's amazing that the radio waves come through, because especially at this point in the development of man, just think of what would happen if radio wave frequency would not penetrate through our atmosphere. Forget your cell phones, right? Forget radios. And also, Forget exploring. Forget seeing the outer, with radio telescopes outside. Forget communicating with your spacecraft. If you go, you can't do it. But amazingly, the radio waves get through, and we can do the communication with the radio waves. It's just an amazing thing. More amazing. The next thing, let's take a look. While we're on the subject of light, I'm going to do this for a little while, just talk about light. Here is a same type of a spectral diagram. Okay, this is the same thing, the wavelength again. This is a short span of wavelength from blue light to red light. So this is just basically just visible. And this is the absorption, not the transmission. This is absorption of light, these lines, by plants, by the elements that produce photosynthesis. And you can see what plants absorb. And the point is, if you go out further either direction, they don't absorb any light. It turns out plants also function just on visible light. And the reason it's green is because they don't absorb much right here, see? They absorb the blue, they absorb the red, they don't absorb the green, so it bounces back, and that's why we see green. That's why it's green, okay? The principal source of oxygen in our atmosphere today, we don't have cyanobacteria, it's plants, right? They produce the oxygen, we breathe in their oxygen, we breathe out the carbon dioxide, they take our carbon dioxide and give us their oxygen, right? That's our wonderful cycle. And again, it's tuned to light. All the factors are tuned to work together. One more diagram on this note we're going to go to, and we're going to do in just a minute. I guess I got that coming up next. Yep, here it is. Okay, this is water, and it's the same sort of a diagram. I told you I was going to do this several times. And this is the absorption, just like the last one, the absorption of energy by water with the light spectrum put in there so that you can see it. And you can clearly see that that this is the low energy part, and that's the high energy part over there. You can clearly see that water allows visible light to go through and absorbs the radiation on both sides. Now you could probably tell if you look very carefully that it absorbs a little more red than blue, right? A little higher here, a little lower here. What color is water? Blue. That's the reason, right? Because the way it absorbs. But the point is, again, in this curve, water transmits visible light, just like the air. Everything is tuned. Everything's tuned for the light that the sun gives us, and to give us what we need, and to prevent us from getting what's going to hurt us. Just more of the magnificent design that's there. Okay, that's so much for light. Let's go to water, okay? I already told you about its light transmission. Let's look at other aspects of water. We tend to think of water as a mundane substance, huh? It's just so readily available. We use it, we get rid of it. And yet, the reality is that water is the most amazing substance in the universe, elemental or compound. Water is the only substance that exists in all three states in our world: solid, liquid, and gas. There are many other compounds called oxides like water, which is combinations of oxygen and other elements, but none of them have any of the properties that are like water. It's the universe's most versatile and most functional compound. And almost all the properties I'm going to be telling you about are just critical to our body's functioning. The first property I'm going to talk about is something that probably seems boring in a way, but it's really important, and you'll understand this when you see this. I'm going to play a video for you to talk about the thermal properties of water. Our bodies are a very complex system because we're warm-blooded animals, which gives us tremendous advantages in being able to do so many things and to live in different climates. But I don't have to tell you, you all know this, is that we have to maintain our body temperature very closely, right? We can go in temperatures of real extremes, but our body temperature can't change but a little bit, or we get really ill, right? We have to find a way to maintain our water temperature. Water is deeply involved in doing that. I'm going to play this for you.
But perhaps the most striking features of water that make life possible are its thermal properties, which help us deal with the impact of heat. Many biochemical processes essential for life can only operate within a narrow band of temperatures. If the temperature is too high or too low, these biochemical processes cease to function, and life like ours becomes impossible. Thus, maintaining stable temperatures on the Earth and inside our cells is essential for us to exist. Water is critical to maintaining stable temperatures. Water has a high heat capacity, which means that it can absorb large amounts of heat with only a relatively small increase in its temperature. You can see this in everyday life. Walk barefoot on sand on a hot summer's day, and you'll likely burn your feet. Place your feet in a swimming pool during the same summer day, and the water will only be pleasantly warm. Water's high capacity for absorbing heat helps both our planet and our bodies to maintain a stable temperature range.
You have to put a lot of energy into water to change the temperature. That's very convenient. It means it's very easy for warm-blooded organisms like ourselves to maintain body temperature. So that's a property of water which seems specifically fit for beings like ourselves.
Another property the water has is what's called latent heat. Another very unusual property, which latent heat is the energy it takes to go through a phase change. In other words, when water is in the form of ice, it has to absorb a certain amount of energy to be converted into water. Similarly, to go from water to steam, you have to absorb a certain amount of energy. Or going backwards, the other way, you give off a certain amount. Well, it turns a lot, yeah. It turns out that water's really an extreme in this case. It takes a huge amount of energy to change the state of water. That too turns out to be.
And but there's another property of water which might even be more critical, and that is that in fact the evaporative cooling of water is one of the greatest of any fluid that's known.
The human metabolism produces large amounts of heat that needs to be discharged, or the body will overheat and die. The evaporation of water through perspiration is one of the key ways our body gets rid of excess heat. Water is especially fit for the task of cooling us because it absorbs a large amount of heat when it evaporates. In fact, more heat is absorbed by the evaporation of water than by the evaporation of almost any other known fluid at ambient temperatures and pressures. Water is uniquely suited to help us shed excess heat in hot climates. When the outside temperatures exceed the level of your body temperature, other ways of getting rid of heat won't work.
Because the only way to lose heat when the environment around you is reaching sort of 38 degrees centigrade is by evaporative cooling, because you can't radiate the heat out because the environment is 38 degrees, it's warmer than you, right? So it's absolutely critical to warm-blooded organisms like ourselves that the evaporative cooling of water is very high. It's one of the highest of any known common fluid.
The high evaporative cooling of water appears to benefit humans more than any other animal. Being relatively hairless, humans lose heat through evaporative cooling more efficiently than any other mammal. Consequently, in the heat of the day, humans can exert themselves continuously for longer periods of time than other mammals.
Okay. I'm going to skip this one here in the interest of time here and go on. The last property of water here I want to talk about is the viscosity of water, the thickness of water. And you could just see in that image just water on the left and then some oil and then maybe some tar that's over there. So everybody has an idea of what viscosity is, thickness. It turns out that water has one of the lowest viscosities of any liquid we know of. And it turns out that this is absolutely another vital property of water. It's really important when you consider the design of our bodies, because we have everything we do, we associate with life, eating, drinking, breathing. Every one of the 30 trillion cells in your body has to do the same thing. It has to breathe. It has to take in nutrients. It has to get rid of the byproducts that it's done using, just like you have. And it has, in the process of doing that, 30 trillion times requires a system of circulating the air and the fluids needed to provide the cells what they need and take away their waste products. That system is the system which we all know is blood, but it's based on water chemistry. And because the whole process that takes place is one of diffusion, which is just a migration across a barrier, across the membrane of your cells, is how all the stuff gets in and gets out. It turns out that there's some engineering here for you engineers, and that engineering is really, really critical. It turns out that the diffusion rate is something like the cube of the distance. The speed is trying to think. It's the cube of the distance. I can't remember the relationship, but it's a power function of the speed at which it diffuses. So for that diffusion to take place across that interface, you have to have a very, very tiny cell with a very tiny membrane. You got to have lots of cells, and you got to have lots and lots and lots of capillaries carrying all this stuff to and away from them. In our bodies, we have 25,000 miles of capillaries serving that. The slightest increase in viscosity would mean that the diameter of those capillaries would have to increase. This one I know is a fourth power function. In other words, if you double the viscosity, you have to have 16 times the width of the capillaries, and we wouldn't have any room for our organs or anything like that. So it's just absolutely critical. Another property of water is its surface tension. This is really important for plants. If it weren't for the surface tension of water, which we all know, you can see the insect there in the water, if it weren't for that surface tension, there would be no way for a tree to get the nutrients up to the leaves. The cells all pull it by using the surface tension property of water. That's absolutely vital to us. Another wonderful property of water is it's the near universal solvent. Almost everything will dissolve in water. There's no better solvent than water. And when you get all done, water is just an absolute wonder. You ought to be like that little child, just on seeing it. Very quickly, I just want to go and wrap up here with the moon and talk about it. It turns out that the moon that we have is absolutely unique. There are planets in our solar system, no other terrestrial planets, that have a moon even remotely like ours. Mercury and Venus have no moons. Mars has 2 tiny little moons, and even the exoplanets that are being discovered don't have them. Our moon has got a great history. and the impact that the moon has on us, that's a history that is extremely rare, that is just one of the most fortuitous circumstances that there was this collision 30 to 100 million years after our solar system formed. But the other thing about our moon is that it has so many impacts on us. I'm going to play one more short video for you on what would happen if the moon disappeared.
What if one night the moon simply disappeared? Would we miss it? Right now, Earth tilts on an axis at 23.5 degrees, mostly due to moon's gravity. If the moon disappeared, Earth's axis would wobble between anywhere from 10 to 45 degrees. Some experts estimate that Jupiter could help keep Earth's tilt from reeling completely out of control. But even just an extra 10-degree tilt could wreak havoc on the climate and seasons. In the past, Earth's tilt has changed by about 1 to 2 degrees, which scientists think could have caused ice ages in the past. It's hard to know what a 10-degree or 45-degree tilt would do, but probably nothing good for most life on Earth.
Our seasons and our evolution and the history of life development on this planet would have been terribly different if it were not for the incredible stability that this planet has. None of the other planets in our solar system, none of them, have the stability that the Earth has. We have it because of the moon. It's kind of like there's this. The reason that it's so stable is this. It's called in physics angular momentum. What it's like is training wheels on a bike. It's keeping you stable, and that's what the moon is doing for us. This really, really big moon. It's also the tidal effects from the moon and the impact on evolution and the growth in the tidal areas. All of it's huge. And then finally, one last thing. I talk about the teleological impacts. Our ability to look out into the universe is part of our purpose. There's something great out there. And it turns out that, remember, the moon was started out very close to the Earth. It's moving away, by the way, at the rate of a little over 1 inch a year from the Earth. So it's not going to be long. But right in this phase, when mankind has appeared on Earth in the history of Earth, just then the moon is in a position where it's about 1/400th the size of the sun, and it's 1/400th the way between the Earth and the sun. Just perfect for it to provide a lunar eclipse. Just for a while in Earth's history, and we're here. And by the way, if it weren't for a lunar eclipse, Einstein's theory of relativity would have never been confirmed by Arthur Eddington, because it was key in proving that the sun bent light, that you could only see bent during a solar eclipse. Eddington saw that. He went out to an island off the coast of Africa to view it and recorded it. So everything is so tuned. So these are just a few things that I looked at that picture of Apollo 8 and saw, okay, those are some interesting things. There's a whole bunch more that we can talk about, and we'll do some more next week. Okay? That's it.